This related rates example says a conical paper cup is 10 inches tall with a radius of 15 inches. The cup is being filled with water so that the water level rises at a rate of 3 inches per second. At what rate is water being poured into the cup when the water level is 2 inches? So what I want to do at this point is I want to draw my cup. I know that the radius of my cup is 15 inches, and I know that the height of my cup is 10 inches. Now I'm going to go ahead and draw my water. So there's my water in my cup, and the radius of my water, I'm going to label that R since the radius of my water is changing, and then the water level or the height, I'll call that H. Now, if I thought about these two-dimensionally, what's essentially happening is I have two similar right triangles. So this triangle is representing my water cup, where this is 10 inches and this is 15 inches. And then the water itself is looking something like that, where the height of the water is H and the radius of the water is R. Now, we care that these are similar triangles because we can set up a relationship. And the relationship is that H over 10 is equal to R over 15, because these are proportional to each other. So that relationship is going to help us in a bit. Now, what I want to do is I want to go ahead and take a look at the volume of a cone. And the formula for the volume of a cone is 1/3 pi r squared times h, which is the height. Now, eventually we're going to need to take the derivative of this with respect to time, but it would make things easier if we could get this down to a single variable. Now, which variable should we get this into? It says here that the cup is being filled with water so that the water level rises at a rate of 3 inches per second. That is another way of saying that dH dt is equal to 3 inches per second. So, because we're given dH dt, it might be helpful if we can get our volume equation only in terms of h. So I'm going to take this equation that we had earlier and I'm going to solve it for r. If I multiply both sides by 15, I get that r equals 15 times h over 10. And if we reduce that, we get r is equal to 3 over 2h. Now what I want to do is I want to go ahead and plug that into my volume formula and replace r. And let's just go ahead and get that simplified. So if I square 3/2, that's going to give me 9/4. And then if I square h, that'll give me h squared. And I still need to multiply by h on the outside. Now 1/3 times 9/4, that should give me 3/4. I have my pi, and then h squared times h is h cubed. At this stage, we can take the derivative. So I have dv dt is equal to 3/4 pi is a constant, and then I can take the derivative of h cubed with respect to time. So that's going to be 3h squared, and then I need to multiply by dH dt. And remember earlier, we said that we had a value for dH dt, and if we go back up here, we said that dH dt was 3 inches per second. So that's the rate at which the height of the water is changing. And we also want to find the rate of change of the volume of the water when the height is equal to 2 inches. So I'm going to go ahead and plug in a height of 2 into my formula. And then I know that also my dH/dt value we said was 3 inches per second. Okay, so let's get this simplified. I have 2 squared, which is 4, and I have a 4 in the denominator, so that 4 and this 4 should cancel out. Now you can see that we are left with 3 times pi times 3 times 3. And if we simplify that, 3 cubed is 27, so we should have 27 pi. And we're looking at the rate of the change of the volume. And so the units on this are going to be cubic inches per second. And that is our final answer.